Hey everyone, welcome back. Today we are diving into a topic that's super important when working with multi-threaded C++ programs: false sharing and cache line awareness. These two terms may sound like academic details, but trust me, they can have a big impact on your program's performance. By the end of this, you will know what false sharing is, how it happens, and most importantly, how to avoid it using simple techniques in C++. Let's get started. So, what is false sharing? To understand false sharing, we need to first talk about how modern CPUs handle memory. CPUs use caches, very fast memory that sits close to the CPU core. These caches load data from RAM in blocks called cache lines, typically 64 bytes in size. Now, here is the key. When two threads on separate cores access data that happen to lie within the same cache line, even if they are working on completely different variables, the CPU treats it as if they are sharing data. So if one thread writes to its variable, the other thread's CPU core sees that as a modification to the shared cache line and invalidates its own copy. That means it needs to reload the data from main memory or another core's cache, and this introduces latency. Let's look at a simple code example that demonstrates this problem. At first glance, it looks fine. We've got two threads incrementing two separate atomic variables. They are not accessing the same variable, so there shouldn't be any contention, right? But here is the catch. If A and B happen to lie on the same cache line, the CPU treats them as being in the same memory block. So every time thread 1 updates A, the cache line that holds both A and B is invalidated for thread 2, and vice versa. This constant back and forth creates what's called false sharing. It's false because the threads aren't really sharing data intentionally, but the hardware sees it differently due to how memory is physically laid out. So how do you fix this? You introduce padding, extra bytes that separate variables onto different cache lines. Here is how we do that. Now, A and B are guaranteed to be on separate cache lines because we have manually padded each one to occupy a full 64 bytes. This eliminates false sharing because no cache line is shared between them. You might be wondering, isn't this kind of micro-optimization premature? And the answer is not always. In high-performance computing, low-latency financial systems, or even general multi-threaded code that processes a lot of data in parallel, false sharing can kill performance. Let's take an example where this shows up very clearly. Imagine you have an array of structs, and each thread works on its own index. Now you spin up 4 threads, each passing its ID from 0 to 3. They are working independently, but guess what? These counter structs are likely stored contiguously in memory, which means some of them may fall on the same cache line. Boom, false sharing again. To fix it, we apply the same padding technique. Now each counter sits on its own cache line. No more unnecessary invalidations. Let's talk briefly about the alignas keyword. It's a C++11 feature that lets you specify alignment requirements for your struct or variable. Here we are aligning the struct to 64 bytes, the size of a typical cache line. You can also use stud hardware destructive interference size, which was added in C++17 to make this a bit more readable and portable. Same effect, cleaner syntax. Now, here is where cache line awareness really shines. When you design data structures with cache lines in mind, you reduce unnecessary contention and improve memory throughput. That means faster execution and better scalability when you add more threads. But it's not just about avoiding false sharing. Sometimes intentional sharing is good. For example, if multiple variables are always accessed together, placing them in the same cache line can improve spatial locality. But when they are accessed independently by different threads, you want to separate them. Let's say you are building a thread-safe queue. You have a head and the tail pointer, both atomics, used by producers and consumers. In a single producer, single consumer setup, the producer updates tail, the consumer updates head. These updates are frequent, and independent. But again, if they are on the same cache line, it's going to hurt performance. Same story, it's false sharing. The fix? Now each member gets its own cache line. Problem solved. But be careful, don't just go throwing 64-byte paddings on everything. Padding adds memory overhead. Use it when it matters. Typically on hot paths where multi-threaded updates occur at high frequency. Also, cache line size isn't universal. 64 bytes is typical for a 64-bit system, but on some platforms it could be different. If you want to future-proof your code, use STUD hardware destructive interference size to align or pad accordingly. Let's wrap this up with some takeaways. False sharing happens when threads access different variables on the same cache line. It leads to performance degradation due to cache invalidations and memory synchronization overhead. You can avoid it by aligning and padding variables so they reside on different cache lines. Use alignas 64 or STUD hardware destructive interference size for safe and portable alignment. Don't overuse padding, apply it where profiling shows contention or where high-frequency updates happen. Cache line awareness is one of those low-level optimizations that becomes critical at scale. If you care about squeezing every drop of performance out of your multi-threaded C++ code, this is something you can't ignore. That's it for today. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one.